So I wanted to talk a little bit about the voting mechanism design, and it's something else that we can adapt as part of RetroPGF in round 2, round 3. Might be interesting. So what is RetroPGF? I mean, we all know what RetroPGF is. It is a capital allocation problem. You have a bunch of projects and you would like to assign funds to those projects, a limited set of funds to them based on some criteria. How much impact did they have? Maybe close the impact gap, etc. So that's what RetroPGF is. What is the process to get there? We have applications, badge holders, which are purposefully here represented by diamonds because they are kind of the key to the RetroPGF process, right? They're making these high-value decisions on how much funding each project should get. You do some sort of aggregation of what the badge holders have done with the applications, and then you decide to distribute the funds. So that being said, just a quick little bit more detail into Filecoin's process, Filecoin 1's process. So the way it worked for badge holders in Filecoin 1 is an approach that's called quorum and threshold, and we've discussed these parameters. But just as a quick overview, the badge holders were presented a view of all of the projects, and they were supposed to take in all of this information simultaneously and make a decision on how much to vote for each project. And then, these votes were aggregated. So the key point that I'm kind of stating here is that they had to make this decision by looking at all of the projects simultaneously. So cognitively, that may be difficult, and it may not lead to optimal results. So the question is can we make this process better? And what does better mean? We have to define that first. And better can mean at least these three things, probably more. We would like better outcomes for the same effort. And by effort, I really mean badge holder effort. So this curve on the right is, I'll get to this curve, but on the x-axis is badge holder effort, and on the y-axis is how well the mechanism is working, in which case, meaning how well is it allocating funds to where we think they should be going. So we'd like to increase that as much as possible, because badge holders are busy and they volunteer their time to do this. And we'd also like to have a more robust mechanism. So what is meant by robustness here is badge holders are given a lot of trust in the RetroPGF process. They are allowed to make whatever decisions they want in terms of voting. And while they do, they are subject to auditing. But that being said, it's very hard to determine whether any sort of negative behaviors occurred. And that can mean like conflict of interest, or it can mean colluding with other badge holders to try to boost a certain project. So we'd like to make the mechanism, the voting mechanism, more robust to those kinds of negative behaviors, and accurate capital allocation I already talked about. So the RetroPGF 1 used a method that we can label as global assessment. And we wanted to see whether, well, there are many other voting mechanisms in the literature. Another one is a pairwise mechanism, and I'll explain the pairwise mechanism in a second. But the hypothesis is that we can basically be more efficient with badge holders' time and with a pairwise mechanism. So we wanted to explore that a little bit. So how does pairwise voting work? So instead of the badge holder being presented with all of the projects simultaneously and then having to make decisions, they get a view, and a view is defined as a pair of projects. So suppose there's a 3-project round. In this case, the badge holder would have to make 3 decisions. And in each decision, in each view, they get presented 2 projects, and they're supposed to vote which one they would rather get funding for. So it's kind of like these two projects are playing a game, maybe a game of chess. One person wins, one person loses. And the chess analogy is important. And we can do this for all of the projects. And then from this, we can use some sort of estimation algorithm to create a global ranking of all the projects, which is what we were doing with the global assessment method. But we're basically asking people to do that directly. And so, hey, look at this cadre of 200 projects and make a global ranking assessment. In this case, we're saying, don't do that. Just look at 2 projects at a time and do this, ideally for all the projects, but I'll explain why that's probably not possible. But for a subset of the projects, and then we'll use some sort of estimation algorithm to come up with a global ranking. So that is the pairwise voting method. Go ahead, Steph.
This is the kitten war method.
A what?
Do you remember kittenwar.com? You got shown 2 pictures of cats and you had to vote which one you thought was prettiest?
Yeah.
But also, more seriously, this addresses another thing which, as a badge holder, I had 106 projects in the list. I deliberately started and did it in reverse of alphabetical order because you inevitably give more attention to the projects near the top of the list, and then you get a bit fatigued as you get towards the bottom. Exactly. And this addresses that.
Exactly. Yeah. So that goes back to your point here of how much effort are you able to expend to do your badge holder duties, and how efficient can we extract a good signal from that? So yeah, exactly. I knew there was some website about pairwise comparisons. I just forgot which one it was. So this is the pairwise voting mechanism. Let's just talk about scaling real fast. So if it scales quadratically, so the number of pairs that you would have to compare if you had 100 projects is basically 5,000. And it gets exponentially bigger. So it is impossible for all of the batch. Well, it's possible, depending on how much time you have. But it's difficult to exhaustively vote on every single pair of projects. But that's okay, because we have inference. So we have, so we can use this. This is one estimation algorithm of many that can basically translate. What we should really think about is we have a bunch of pairwise votes, and we're going to take that and create a global ranking. We can do that with models. One model is the Bradley-Terry model. And how this model works is if I have project I and project J, and project I wins, or player I wins, then player I has this score, and player J has a score. And what I'm trying to do is infer the true scores of each player from this list of pairwise rankings. This Bradley-Terry model is a way to do that inference. And it's nice because we can do that inference with a subset of data points. And I'll show some initial simulation results on this. And that's where we are here. So this is my final slide, and then we can open it up for discussion. But what we did in order to kind of test out this is we built on a simulator that Carl from Open Source Observer had built, which models the global assessment method. And what we did was we built a pairwise assessment method. And I will explain the variable. Let's go to the plot on the right first, and then we can backtrack our way into what it means. So on the x-axis here is what we call badge holder expertise. So if a badge holder has an expertise of 0, that means they're basically making effectively random decisions. So they're not an expert, but they happen to be a badge holder and they're voting. And a badge holder with an expertise of 1.0, right? This is just an arbitrary scale, but if they're 1.0, that means that they're making perfect decisions all the time. Now, the interesting thing about pairwise voting that is different than the global assessment is that when you're presented with a pair of projects, it's easier to make a decision on which project should win if the impact delta between them is high. And if the impact delta between them is low, it's harder to make a decision, right? So there's actually kind of 2 dimensions that you need to kind of model a badge holder's behavior on. And that's what this graph on the left is showing. It's basically saying as the delta in the project impact goes from 0 to 1, the probability of making a correct decision increases. Now, how that scales with that also scales with the expertise of the badge holder, which is why there's different lines here. So like a badge holder with an expertise of 1, they can discern which project should win no matter what the project delta, no matter the delta between the impacts of the projects. For others, it's much harder. And these functions are one way to model that. There may be more accurate ways to do it. So that's how we model the expertise of a badge holder. And then what we're doing, right, in pairwise voting is we're trying to build a global ranking of all of the projects from a bunch of pairwise decisions. So the metric that we use, and we can use different metrics, but one way is called a rank correlation, where we basically say, instead of correlating on the actual numbers, you correlate on the ranks of the scores and how that aligns to the true project's impact. Since this is all in simulation, we can simulate projects with different impact levels, and then we can say, how well does it align? And that's what the plot on the, now coming back to the plot on the right, we're showing for different levels of expertise and how well does it align. Now, the final dimension that's shown in this plot is a parameter called the laziness of the badge holder. And the reason we have that in there is because of this. So we talked about how if there's 100 projects, badge holder, an exhaustive badge holder would have made 5,000 decisions, 4,950. So let's say they make half of those decisions, and then they say, okay, I'm done. So that would correspond to a laziness of 50%. 75% means they only vote on 25% of the projects, and so on. So what this is showing is that this, yeah, go ahead.
Is laziness like, just so I'm clear, is it like you make the decision with like complete concentration and expertise for 50% of them, and then you just stop? Or are you like degrading during the experience?
That would be an interesting thing to model. What is done in here is the badge holder has a constant level of expertise throughout the voting process. We can decay it.
Okay, right.
Which
Thanks.
probably makes sense. Go ahead.
So I guess 2 clarifying questions. It looks like you're trying to get a total ordering of projects and identify the underlying, like an objective ordering. Some of these voting mechanisms also handle the case that you've got a different subjective total ordering per badge holder. And so you can try and identify the individual total ordering of each badge holder, and then you can come up with the agreed sort of compromise ordering across badge holders as a secondary step. Is there a reason you would do one versus the other?
I'm trying to parse your question.
So you can have someone who's voting do a bunch of pairwise and get their total order, which is their subjective view of the right order. And that's going to be a different total order than another badge holder.
Yep.
And then you've got a question of what is the sort of compromised total ordering that all of the badge holders would agree on in this second aggregation step. Versus having a bunch of individual pairwise votes. So by all of your badge holders that you just sort of combine into a single thing and trying.
That's what this is.
Yes.
So this is basically taking all of the badge holders and combining all of their votes into one, and then doing an estimation. Another way would be what you said, which is every badge holder has their own ordering, which we call subjective ordering, and then you have to figure out how to take that and aggregate it together.
So the main thing, and I think there's a deep literature here that I imagine can be drawn on. You either are going to have each badge holder do a fixed number of comparisons so that they're fairly weighted. If you just have sort of an open, you can keep doing your comparison, then the people who spend time doing more comparisons will get more influence in the overall order if you just combine it purely across all votes. Whereas if you get to a total order per badge holder, then by doing more votes, I refine my subjective total order, but I don't get undue influence in the overall total ordering.
Sure. Yeah. I mean, that's a good point. I think we would need to look at the literature to understand what is optimal, and probably under different conditions. I don't know off the top of my head. Yeah, but that's a good point. Yeah. So we're doing some initial experiments on this. What is it showing at a very high level? What it's showing is that, at least in the way that we've done it, which is aggregated all of the badge holders into a single pool and then done an estimation, it gets to pretty high alignment even with low badge holder expertise. Now, I want to just caveat that, because low badge holder, the number 0.25 seems low, but it really just depends on how I've mapped that function here, which is the orange line. Like I could map it differently. So this is a subjective thing that we're translating into some function that we need to determine whether that actually makes sense or not. But it may be more helpful to understand the initial ramp up from 0 to 0.25. How fast does that change? I think that's probably more informative. But yes. All right. Thanks.